Well, greetings, mathletes, and welcome back. Today we're going to be taking a look at another application of integration, which is solids of revolution. Um, Basically, what this is a way of rotating a function around some axis and then getting the volume of the shape that results. So I can already tell that this is going to be very difficult to explain with just a verbal explanation. So let's go ahead and take a look at the whiteboard here. Um, yeah, there we go. Okay, so here's the idea. So, and this will be our first example also. So let's say I have the function f of x is equal to the square root of x, right? Um, now let's make this a little bigger so we can see the detail. Right, we know that function looks something like this, right? And it keeps going on forever. Um, Now, we're told that we want to find, we want to create, in fact, I'm not going to give it limits of integration yet, but we want to carve out some area here, like so, and rotate this curve around the x-axis so that I end up with something like this, right? So we have this cup shape, right? And we can go inside this and take a look at it and all that stuff. But we do have to have a place to start and a place to stop, right? Um, so let's see how we can get a hold of this volume, because well, it's a square root function, so it's half a parabola. So this is basically a parabola rotated around an axis. So let's take a look at it. One of the things that integrals do is it adds up little rectangles, right? You find the height of the rectangle and the width of the rectangle is your delta x. Well, this time, instead of rectangles, what we're going to be finding are discs. So we're going to take this and we're going to take a look at it as if it's a little disc carved out of this. And this is what we're going to be adding up, because we can get a whole bunch of these, right? I can start stacking discs on this. And I can make up this entire volume with those discs. So how do we get a hold of that volume? Well, let's look at what it takes to find the area of one of these discs. So I need the surface area of the disc, which is a circle, times the width of the disc. So I need the surface area of this times the width of the disc, which is delta x. Okay, so if I'm going to add all of these up in fact, let's just pick some numbers here. Let's say this is at 2, right? We're looking at this area from 0 to 2. Sometimes one of the boundaries is natural, like the function just ends, so you know that's where you need to use it. That's where it needs to start. But if we look at the area of one of these discs, remember the area of a circle is pi r squared. Okay, so the pi is a constant, it's not going to change. But the r, well, as I move across this thing, r is going to be different, right? The r that I have, the radius I have at this end, is going to be totally different than the radius I find down here. Right? This is going to be a different radius for this disk. So we have to be able to get this radius to fluctuate the way it's supposed to. Well, the height of any of these is the value of the function at that point, right? That's a point on the function, so the distance from here to here is the radius. So the radius, in this case, is the function. So r is equal to the square root of x. So we're going to put that in, and it's pi r squared, right? That's just the surface area of the disk. If we want the width of the disk, that's our dx. And if we want to add up all the rectangles, it's the integral from 0 to 2. Okay, so this is, let me clean that up a little bit. This is the integral from 0 to 2 of pi times the radius squared. So what I'm doing is with this integral is I'm adding up all of these disks all the way across this shape. So let's go ahead and handle this now. That's a 0, not a 6. Okay, so we can pull the pi out. So I can look at it this way. From 0 to 2 of, well, the square root of x squared, the square of the square root of x is just x. And since this, it's actually, well, it only takes in positive values into the absolute value, so we're still okay. You do have to think about the sign of this thing sometimes. And that's a pretty straightforward computation. The integral of x dx would, let's see, that's going to be pi times x squared over 2 evaluated from 0 to 2, right? Oh, I see what I did. I actually changed it from my example. I did 0 to 4 in my example, so this isn't going to be the same answer. Nonetheless, this is my function. So all I have to do is evaluate it. I just used the fundamental theorem of calculus. And so we evaluated at f of 2, and then we evaluated f of 0. So we have pi times 2 squared over 2 minus pi times 0 squared over 2. Well, that's going to die. So what we end up is 4 over 2 or 2. So this is 2 pi, which I find very interesting, right? So the volume of this thing, this crazy shape, this parabola that's been spun around the x-axis, is 2 pi. That's amazing how that pi shows up everywhere. Now, I want to point some things out too. So if you were given this problem from the beginning, I spent some time just talking it in, but what you would be given, it would look like this. Let's see, find somewhere I have the room to write it. Yeah, it would say something like, find the area defined by f of x equals the square root of x between 0 and 2. Well, they would say x equals. No, that doesn't look right either. Thought maybe that would. Anyways, that's the x. Between 0 and 2, revolved about the x-axis. Right, so that's basically what we did. We revolved one of these shapes around the x-axis, and then we computed the volume. And so these things are actually called, if I could spell, solids of revolution. Right, so that's what we're computing today, is solids of revolution. So I really think it's a very important thing to be able to draw a decent picture. So take your time on your picture so that you can attach the formulas to the right things. Right, that's what the picture helps you do, is to build your disk, because that's what this is. We're basically cutting out a big disk and finding its area. Okay, so let's go ahead and take a look at the second example then. Oops, that is the wrong thing. There we go. That's what I meant to do. Okay, so here's our next problem. We want to find the volume of a shape bounded by x squared plus y squared equals 9, where y is greater than or equal to 0, revolved about the x-axis. Okay, so we have to piece some things together here. First of all, we need to know what this shape is, and that's a circle, right? That's the form of a circle. A circle in the square root of this number is the radius of the circle. So this is a circle with radius 3, centered at 0, 0, because if it was centered anywhere else, it would be x minus something squared and y minus something squared. Okay, so this thing looks something like this. And it's a circle, but it says y is greater than 0. Y is greater. I'm going to try that part again. That's getting bad. Okay, let's try that again. But y is greater than 0, so it's the upper half of the circle. Right? So we're looking at that. And now we're rotating it around the x-axis, which means that really what we just did when we do this is we created a sphere. Right? That's really what we're looking at. We just created a sphere. Now, what we want from this sphere, and I'm going to move that little diameter or the circumference off of this because it's in the way. We need to be able to carve a disc out. Okay, so if we're going to carve out a disc, let's look at the height of one of these discs. I think this is one of the more valuable things that comes out of looking at the rectangle sums, is that setting up these little individual things that you have to add up really sets up your integral. So I need one of these discs, right? One of these guys. Oops. Okay, so I need the height of the disk. I already know the width of the disk is delta x. Or my dx is what it ends up becoming. So I just need the radius. I need to find the radius so I can plug it into that integral. The radius is the height at this point. And the only way we're going to get this is if we go ahead and solve this for y. So if x squared plus y squared equals 9, I need this y value here, so I'm going to go ahead and just solve this for y. So if I go ahead and subtract the x squared over and take the square root, y is equal to, it would be plus or minus the square root of 9 minus x squared, but because we've already been told y is positive, I don't have to worry about the negative. I can just look at it this way. So this is the height. So now we can set this up. We know that it's pi r squared for the area of a circle. So this integral now becomes the integral of pi times r, which is the square root of 9 minus x squared, dx. So that's what I'm working on here. Right? And some nice things happen. I can pull the pi out. Oh, and I also need to figure out my limits of integration too. We'll come to that real quick. So this is pi times, and if I square that, that cancels with that. So I have 9 minus x squared dx. Now my limits of integration will just be the ends of the circle. And since this is a circle with radius 3, that means I'm at 3 and negative 3 here. So this is the integral from negative 3 to 3 of all this. So if we go ahead and integrate, it's going to be pi times, well, the integral of 9 is 9x. The integral of x squared is x cubed over 3. And I'm going to be evaluating this from negative 3 to 3. Right, notice the integral wasn't really the hard part of this. The integral actually goes fairly easy. It's the setup that's the hard part of this. Okay, so we need to evaluate it from top to bottom. So the first one would be, and I don't want to forget about this pi at the end. If I plug that in, that would be 27. So 3 times 9 is 27. Minus 3 times 3 to the third is 27, divided by 3 is 9, so it's minus 9. And then it's going to be minus pi times, and we need to evaluate the other end, negative 3. So this would be negative 27, and this would be positive 9 this time. So they're opposite signs. Okay, well, 27 minus 9 is 18, and this would be negative 18, and the negative, so this, if we go ahead and simplify this, this is 18 pi minus negative 18 pi, which is 36 pi. So the volume of this sphere is 36 pi. And we can actually check that because the volume of a sphere is 4/3 pi r cubed, right? So we can actually just check this out and see how it works. Yes, I know this makes it seem like it's pointless to do this since we have a volume formula for it, but it's nice to have more than one way to find these things. It actually leads to a lot of other results. But yeah, the radius is 3, so if I plug that in, I end up with, let's see here, let's go ahead and check it out. 3, that's 27 divided by 3. That's coming out too big. So this squared, oh, okay, yeah, it does work out. So let's see here. That's 27 divided by 3 is 9. 9 times 4 is 36 pi. There we go. I was doing a subtraction in there instead of a division for some reason. So yeah, we do have the correct answer here. But again, this is all about the setup and getting used to setting things up like this. Okay. So, you know what, actually, before I do the next one, I just kind of want to walk through the overview of this again. So we were handed the problem. We figured out what the shape was that was defined by these equations that we were given, and we sketch it. And once we have that sketch, then we kind of try to envision what it looks like when it revolves around the axis, and we try to sketch that in. From there, it's a matter of just finding out what's going to be a radius. So everything you're doing right now is about finding a radius. So that you can plug it into the formula and integrate. And then once we do that and integrate, that's when the easy part starts. It's because you integrate and it's just pretty much plug and chug from there. Okay, so let's look at the next one. Okay, so this next one is find, try it again, put a little space in there. Find the area enclosed by x plus 2y equals 2, y equals 0, and x equals 0, and revolve it. So we want to revolve it around the x-axis and find the volume of the resulting shape. Okay, so we're going to need to figure out what these equations give us here. Okay, so first, x plus 2y equals 2. So if I plug in 0 for x, I see the y-intercept has to be 1. So this is 1. If I make y 0, the x-intercept is 2. So that's at 2. So that's enough to graph my line. Okay. And then we have the y equals 0. Well, that's the x-intercept right here. Or that's the x-axis, excuse me, not intercept. And x equals 0 is the y-axis. Okay, so what that means is that this is the area enclosed. Okay, so we want to take this thing and rotate it about the x-axis. So let me actually get some of that shading off of there so we can play. So really what we're looking at here is a cone. Because once I revolve this, I'm going to end up with the rest of the shape coming down this way, and I'll be able to carve out a disc from here to here. So you can see the cone in here, right? And so one disc looks something like this, and we need its radius because we already know we have a dx here for our width. So the radius of this thing is going to be the height, the distance between the x-axis and the function itself. So, but I need it as a y value because this is a y value if I'm measuring straight up. So x plus 2y equals 2. If I go ahead and solve this for y, it gives me y is equal to -1/2. Is that right? Yeah, it's -1/2 x plus 1. Okay, yeah, so this would be our radius because the y value is our radius. It's a little more hidden when this equation isn't written as a function. So we have to write it as a function. Okay, so this is our radius, which means our integral is going to be pi times -1/2 x plus 1 dx. And now we need our limits of integration, right? So we need we need to know where this starts over here and where it ends. Well, I can see it ends at 2, and I can see it starts at 0. And I almost forgot here, this is supposed to be squared. This guy should be squared. I almost forgot about that. So we're going to have to square this out too, right? So let's see here. Let's go ahead and square that out, and then we'll take a look at the integral. I'm just going to start by, I'm going to move this. Oops. Yeah, that's right. I moved the wrong thing. I was going to move this pi out. There we go. Okay, so we have to square this. So if we square it, actually this isn't a bad way to do it. This is a little quick review. That's going to give me 1/4 x, -1/2 x, -1/2 x, and 1. So if I add everybody together here, it's now pi times the integral from 0 to 2 of, oh, that's x squared, 1/4 x squared, and then minus x plus 1. Right, so that's our integral now. So now if we take that integral, let's just take this term by term here. Let's see, it's going to be pi times, and then, so the integral of x squared is x cubed over 3, so this is x cubed over 12. And then the integral of x is x squared over 2, so this is minus x squared over 2. And then the integral of 1 is x, and I need to evaluate that from 0 to 2. It's nice when a 0 is in there because, you know, especially when you have x's in every term, because a 0 is going to kill everybody. So if I evaluate this at 2, this is pi times 8/12 minus 4/2 plus 2. Right, so that's what we're looking at. And then minus, and everything evaluated at 0. 0 over 12 plus 0, or minus 0 over 2 plus 0. Right, so that's just going to be a 0. So we just have to worry about this. And if we look at this, 8/12, if I divide both by 4, that's 2/3. This is minus 2 plus 2, so those guys cancel. So this is just 2 pi over 3 for the volume of this particular cone here that we just defined. right? So again, we had to draw a picture. Sometimes you have to massage around the equations a little bit to get them to be what you want, so that you can get the radius you want. Once you have the radius and you have the limits of integration, you pretty much have everything you need to take the integral and find the volume. But it's about finding that radius. That's actually one of the more difficult things to do here. I don't think the picture's too trivial either. It takes some time and patience to draw a good picture, and sometimes it can be very frustrating. Okay, so what I want to do now, which is kind of different, I want to show you, because this is what we're going to actually be hitting in the next lecture, is that you can do these in a number of different ways. What we're covering today is just kind of setting the foundation for what we're going to be doing. We can also revolve this around the y-axis. We can also revolve this around any axis we define. And it doesn't, I mean, and we can change that shape into some things that might be a little bit bizarre. So let's go ahead and do that. Can I do this way? I'll do that. I'm going to clear a bunch of this stuff off, and we're going to change what we're looking at on this. We're going to take a look at it in terms of y instead of x. So switch back to that. I'm not going to say x-axis anymore. I'm going to say it's the y-axis that we're going to revolve this around. So the curve hasn't changed, but what we're revolving it around has. So if I take a look at this, I'm actually going to need to do a little more of this time. Remember this it crossed at 1, and then at the x-axis it crossed at 2, so we end up with this. And this time what we're doing is revolving it this way. Right, so we're going around the y-axis. So our disk actually is going to look a little more like this. Right, so we're looking for this radius right here. And notice that distance, since it's a horizontal distance, that is an x value. And so what we have to do is, normally we write y as a function of x. This time we're going to have to write x as a function of y. So what that means is we're going to solve this for x. So all I have to do actually, well, actually let's start here just so we can see where we started. Right, if I solve it for x, I get x of y is equal to, well, I'm just subtracting the 2y over, minus 2y plus 2. Right, so that's what I'm looking at. So let's take a look at our integral. This time we're going from 0 to 1, right? Because we're going from the bottom to the top. So it's 0 to 1. That's not a 1. I'm thinking about pi for some reason. 0 to 1 of pi times the radius squared. And the radius in this time is in terms of x. So it's minus 2x plus 2 dx. Oh, and then it's squared. I almost forgot to square it. Okay, so let's go ahead and square this thing out just so we can see what we have. That's 4x squared minus 4x plus 4. That's a lot of 4s. I guess this one's a little more forceful. Okay. So it's the integral from 0 to 1. I'm going to put the pi on the outside, and this is now 4x squared minus 8x plus 4 dx, right? So I'm going to go ahead and move this out of the way because it's going to be causing problems if I don't. Well, 4 is a common factor, so I can actually do this, pull a 4 pi out. And that leaves me with the integral of x squared minus 2x plus 1 dx. So that's a little bit nicer. So now we get, I'm going to start over here, 4 pi. And if we integrate, I get x cubed over 3. This would be x squared over 2. So that's going to cancel that. So it's minus x squared plus x. And I'm evaluating that from 0 to 1. Well, 1s are nice to evaluate because everybody turns into their coefficient. And 0s are nice, and all of these terms have x's, so that 0 is not even going to evaluate. So this is now 4 pi times, that's 1/3 plus 1, or excuse me, minus 1 plus 1. I said that backwards. So minus 1 plus 1, so those cancel. And then it's minus 4 pi, and then that other one evaluates to 0. So this ends up being 4/3 pi. Right? So we got a very different area when we worked it out from the other side. Okay, now that was more of just a little peek into what's coming up next here. But we can change the way that this thing is revolved. So again, a lot of this is just being able to see it and piece it together, and that takes some patience. Sometimes you can see it like that. It doesn't take any work at all for you. Other times you'll stare at it for hours and not be able to piece it together without a little bit of help. So if you need help, please come and see me. I'm more than happy to help you. And other than that, that pretty much wraps us up for the day. So until next time, keep your pencils and your wits sharp.